Alrighty, welcome back. In this video we're going to look at loads and stores. Now some of you might have been wondering why there was a slide with a beautiful looking mallard duck. If you're in my tutorials you might have heard me told you already. Sometimes when you're stuck writing assembly programming, you can resolve whatever you're stuck on by explaining your code to someone. Often when I need to help a student, I walk up to the student, they explain their code, and in the process of explaining their code, they work out what they've done wrong. So, the whole idea of the duck is sometimes maybe you just need to explain your code to a little rubber ducky, and in the process of explaining it, you'll get a resolution to your problem. Anyway, I digress. On to loads and stores. Let's fly through some slides here. Okay. Also another quick explanation. Bytes and addressing and stuff. So the whole concept behind the buckets is that you can think of memory as a whole bunch of buckets, and each bucket has a little number on it, and that's its memory address, and each bucket can hold a byte of numbers. So our memory is a whole bunch of buckets, each one holds 1 byte of numbers, and it has its own little label printed on it, which is its address. So yeah, the byte is the smallest addressable unit in our memory. And of course, 8 bits is 1 byte. Okay, loads and stores. So LDR is our load instruction. Just quickly going back to our cheat sheet here. Where can I find all my dudes? Okay, so down the bottom of the first page, we've got our loads and stores here. Zoom. Alright. And we've got our regular LDR and STR. And there's a whole bunch of funky things you can do with them. And we've got some other wacky loads, and we've got index loads and offsetting loads, literal loads, positive stack loads and negative stack loads. But for now, we're just going to mostly look at the simple ones, which are LDR and STR of the offset variety. So I'll get to what all that means shortly. Okay, so this is the basic way that you do a load. So what this is going to do here, reading from right to left, it's going to load from the address specified by register 1 into register 0. So it's going to treat register 1 as a memory address. And just remember, memory addresses are just a number. So it's going to look in memory at the address specified by R1 and put it whatever it finds into register 0. Okay, so this is the syntax. Step. Okay, let's get to our examples. Now, before I start here, a lot of people have asked why in examples like this we've used this hexadecimal number here, which, to make my life simple, I'm just going to call 2 million. So why do we use 2 million when we play around with loads and stores, etc.? Well, in a much earlier slide, this one, we've got the entire memory space of our microcontroller. And it just so happens to be that our 2 million here is the first address of the microcontroller's RAM, or random access memory. So from 2 million to 3 FFFFFFFF, that's all set aside for RAM on the microcontroller. Okay, so that little aside over. It's just a whole bunch of memory that we can play around with, and it's all RAM on the chip. Let's get to our example. Okay, so here's one I prepared earlier. Now, when you're doing stuff in memory, it's often a very good idea to open up your memory viewer so you can look at what's going on. So the first thing we're going to do is put our memory address into register 1. Here it is, our 2 million, whatever it is. Now we're going to load into register 0, whatever's at register 1. Okay, so we have a whole bunch of crap over here. B1 72 4B 08. And if we look over here in memory, well, we've got roughly that. Remember, we're in Little Endian land, so we sort of have to read things backwards. But that's okay. Now, some of you might be wondering why. I just said earlier that our little memory buckets are 1 byte. And when we look here, we've got a memory address. This is the address of 1 byte of memory, specifically this byte here. So you might be wondering why our load instruction has pulled in all this. So by default, loads will load a word or 32 bits of data from memory. So the way that this works is that we start at our 2 million, and then we keep counting along until we have 4 bytes of data. So we have 2 million, 2 million and 1, 2 million and 2, 2 million and 3. There we go. So now we have 4 bytes of data, and we're going to start reading backwards now because we're in little endian. So we have B1, B1 over here, 72, and 72 over here, 4B, 4B over here, and 08, 08 over here. Just to recap, we started our 2 million, we count up until we have 4 bytes, and then we read them backwards and shove them into the register left to right. Okay, so we've done a load. Let's go back to our slides. What value will be in R0? Well, whatever junk happens to be in RAM. Buckets, hooray! Oh, so if you're ever in lecture slides, in the lectures and you see this, it's a little converter slide, you can punch numbers in, it does conversions. Cool. Okay, so before we move on to doing stores, let's have a quick quiz question. Are any of these valid memory addresses? I'll give you a hint. All of them except one are valid memory addresses. And it is a little bit of a trick question. So if you'd like to pause the video here and have a crack at working it out, go right ahead. Okay, welcome back. So we have 3 valid memory addresses and 1 invalid. Now, if you haven't been able to work it out, I'll give you a hint. It's the bottom one that's invalid. And why, you might ask? Well, it's too big. If you look here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 digits of hexadecimal. Now, each hexadecimal digit is 4 bits, so we have 36 bits of number here. And if you remember, our microcontroller has a 32-bit wide microcontroller. So it's too big. It won't fit in our micro. All of these are valid because they're all 32-bit numbers, or 1 point. They can be represented as in 32 bits. You know, they fit inside 32 bits. Okay, so let's look at storing. Now, storing is the same as loading, just the other way around. So what is it going to do? Store at the memory address in register 1 the contents of register 0. Right, let's do an example here. So we're going to put the number 42 into register 0. In hexadecimal, that's 2A. And we're going to make sure our memory address is in R1. So we have 42 or 2A in R0 and our memory address in R1. Now, if we look over to our memory viewer here, we can see there's a whole bunch of random garbage in here. Now we're going to store. And boom, we're in. So, just like our load from before, stores will store 32 bits, starting at our address, and then counting up 1, 2, 3, 4, storing 4 bytes, or 32 bits. And we're still in our little endian land, so we sort of start here, and we store our first 00, 00, 00, and then finally we get to the last byte, and we store our 2A. So here's another one with a bit more numbers. Now, as I explained in the last video, my use of LDR here is just like a big move. So if you put LDR equals, it's like a move for big numbers. So yeah, just imagine this as a move. Okay, so we've got this in R0 and we're going to store it in R1. Right, we're going to store it in the address at R1. There we go. So we've got FFFF, A, B, C, D. So we start at 2 million, we count up till we have 4 bytes of memory, and then we start working backwards. So FF, 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 FF. Then over here, we grab our little AB, we put it in here, we grab our CD, and we put it in here. Lovely. Okay. Okay. What if we don't want to actually load or store 32 bits or 4 bytes of information at once? Well, there are a few handy loads and stores which only do a little bit of stuff at once. So let's look at LDRB first. Now, LDRB is going to load a byte. So it's going to load from register 1, which is our 2 million address, into register 0. So if we go to our memory viewer and we look at 2 million here, and it's only going to load a single byte because it's an LDRB. So we get our 1 byte here, and then we stop. Now, this should load CD into register 0. There we go. So now we have CD. So in this line, I'm going to introduce the idea of doing an offset load. If we flick back to our cheat sheet very quickly here, you can see that from over here, that we're loading from RB plus or minus an offset. So what actually is the offset? But the offset here is an optional small positive or negative constant that you can use to offset the memory address. So what does all this mean? So this is going to load from R1, which is our 2 million number, plus our constant value here, 1. So if we take our 2 million here and add 1 to it, we have 2 million and 1, which is going to be AB. So we'll do that load. And there we go, we've got AB. Because AB is the contents of memory at 2 million, which is our register 1, plus the constant 1. So 2 million plus 1. And here we are, we have AB. So that's all very well and good. We've loaded a byte or 8 bits. Now let's do a half word load. So once again, we're loading from 2 million into register 0. So we'll get 2 bytes. We'll grab our AB and shove it in, and then grab our CD and shove it in. So when we do half words and bytes, we always put it in the lower bits of the register. So that's all very well and good. We've loaded 16 bits, or 2 bytes, or a half word. Yes, there are many different ways to describe a certain number of bits. So we've loaded that from memory into our register. So let's do another offset load. We're going to load a half word from our 2 million address plus 4. So let's look at what this is going to do. We'll take our 2 million, we're going to add 1, 2, 3, 4. So we're going to load from here. Let's do the instruction. Okay, so we've taken our 68 and put it in. We've taken our 4 and we've put it in. There you go. So just remember, when you do these offsets, you're offsetting by a memory address, which is a byte at a time. Unlike shifts, for example, which are bits at a time, load offsets are a byte at a time. Okay. Now I don't think the next slide is anything. Okay, cool. So we can also store bytes and half words. So I'm going to put this into register 0, AABBCCDD. Now someone asked me today in my tutorial where it actually stores the byte from, because there's 4 bytes worth of numbers in our register here. So these byte and half word loads and stores always operate on the lowest byte or half word. So the lowest byte is the furthest right. In this case, it's going to be DD. So we're going to put DD into our memory at 2 million, which is R1. So we'll do that, and we've got our DD here. Now, same thing for the store half word. We're going to store our lowest half word, which is CCDD, at 2 million. So we start at our 2 million. We count until we have 2 bytes, and then we grab CC, we put it in this one, then we grab DD, we put it in there. There we go, so we've stored a half word. Just let me check that there's nothing else I need to cover in this video. Wonderful. Okay, so that's a very quick rundown of loads and stores. I hope this has been helpful for you. Now there's a whole bunch of other interesting stores and loads which you can look at on your cheat sheet, and feel free to play around with in the labs. If you have any questions, just ask your tutor. Oh, and I'll just quickly revisit this. doing LDRs like this. So some numbers are too big to fit in a move instruction, and you can get around that by doing an LDR like so. So what this is really just doing is a move. So we're moving this constant into register 0, but because we put an equal in front of it, it's treating this as a constant and not as a register or anything, so we're just putting this number into R0. And that's on your cheat sheet. Oh, it's not even on your cheat sheet. Wonderful. Anyway, so that's how that works. Thank you for watching the video, and if you have any other questions, please post on Waddle or ask your tutor. Thank you.